So, so this is the data obtained when the culture was glucose limited. And the other graphs that are obtained, uh, like this one over here, the one in black, this is the data obtained when the culture is ammonia limited. And the other one, the one on top of that is sulfate limited, and the one on still top of that is phosphate limited. And I'm getting ahead of myself here, but the people who got this data came back and said, your theory makes no sense. Are you telling me that the maintenance is somehow higher in nitrogen limited cultures as opposed to carbon limited cultures? Because maintenance by definition is something it's like energy being used for non-growth related purposes. And I can see no reason why this would be much higher in nitrogen limited cultures versus carbon limited cultures. And likewise, why should it be so high in phosphate limited cultures? I mean, what's going on? Your model seems to make no sense. So we'll get back to that later on if we get back to it at all. Otherwise, this is a good paper for you to read to see how people build on things. Um, I think I've basically shown you what real data looks like. Hopefully, um, that should be good enough for the time being. Coming back to what I did last time, then um, we first showed that the rates don't match up with what the Monod model predicts, and then we derived the concentrations, and I showed you what the concentrations look like. Uh, the steady state concentration S has this form over here where at very small d it increases linearly and it's very very small, and then as d approaches mu m it goes to infinity. And I'll come back to this in a minute. I want to add a couple of points here that I did not mention last time. These are important points. And the cell density, as I pointed out, is nothing but the yield multiplied by the drop in the concentration from the feed into the concentration inside the reactor. Now, I just want to come back to this formula and sort of explain to you the geometry of the steady state in what I think is a simpler way to understand it, which is, you know, ultimately the steady state concentration of the substrate is coming by solving this equation. Mu m multiplied by S over Ks plus S equals D, which basically says that the specific growth rate has to be equal to the dilution rate. And if you remember, this relationship ultimately comes from the fact that the rate at which the cells are growing is equal to the rate at which the cells are coming out of the reactor. Now, an easy way to understand this equation is to simply look at it geometrically. So just plot the function mu m multiplied by S over Ks plus S, which I have done on the left hand side with a this is the function mu. It's a hyperbolic function that typically rises very very fast because Ks is small and then remains constant at the value mu m. Now, to find out the value of S at any particular d, you simply draw a horizontal line as I have drawn in red at any particular d. See if I can blow it up. No, I can't blow it up anymore. I hope you can see the picture. Just draw a horizontal line of magnitude d, and wherever it cuts this curve is the point at which mu is equal to d, because that's the definition, right? That's what the equation is saying. Mu is equal to d. So, for example, if I take any particular d, I get this intersection point. And then if I take a slightly bigger d, I get a slightly bigger intersection point. And if I make it bigger than mu m, then you can see there is no intersection point at all, which is exactly what is predicted by this model. There is no positive uh, intercept. Yeah. The, now, once I have done this geometrically, you can actually see that the graph that we are getting. So basically, start staring at this graph from the left hand side. Okay, so let me draw these arrows once again. Start staring at this graph from the left hand side. If you stare at this graph from the left hand side, you can see that basically this graph is telling you, if I give you the value of d on the y axis, it is giving you the value of x. Sorry, it is giving you the value of s on the x axis. All right. So this graph that you are seeing over here is nothing but this graph, right? Viewed from the y-axis, right? You stare at it, and whatever the graph looks like, you will get it over here. Have I made the point clear? I mean, I think it's so. So, if you understand y on the left-hand side, if you understand the fact that mu rises very sharply with s and then flattens out, then you can see why this function s equal to ks multiplied by d over mu m plus d will basically be a flat function that just goes up very fast. So on the right hand side, if you view the graph from here, left hand side, from the y axis, you are basically seeing exactly the graph mu m multiplied by s over ks plus s. Is that part clear?
Yes, sir.
And the second thing I want to point out, which is sort of the important point, is um, that the the substrate concentration goes up and becomes infinitely large as d approaches mu m. But it approaches the value sf at some d smaller than mu m, right? You can see that, right? The way it is drawn, it is hitting sf at some value of d smaller than mu m. And at that value of d, when s becomes equal to sf, you basically are saying that the concentration of the substrate in the reactor is equal to the feed concentration. So nothing is being consumed, right? Whatever comes in stays put. And that means that your biomass concentration, you can see it from the formula here, x equals ysx multiplied by sf minus s. If s is equal to sf, then x is equal to 0. So at this d, which is close to mu m, your substrate concentration becomes equal to the feed concentration, and the biomass concentration becomes equal to 0. Now, my question to you is, can you, by looking at what we have done, tell me what the magnitude of that D will be? So basically, I'm asking, what is the value of this D where S becomes equal to SF and X then therefore is equal to 0? What is the value of D, of that D? I mean, based on what I have just said, I just told you one way to view it is, I just said, did you understand that this graph here is nothing but mu plotted as a function of S as you view it on the y-axis? Actually, let me just give you the result. This D will be mu m multiplied by SF divided by Ks plus SF. And this is actually called the critical dilution rate. Called the critical, or wash out dilution rate. Now, having given you the solution, can you see why that should be the case?
So I didn't get why is this called the washout
No,
dilution?
no, no. Don't worry about what I'm calling it. I'm saying, does the formula make any sense to you now?
So yeah, that it does, but like one thing I didn't understand, like why do they call it the critical dilution? Like what is the physical significance of?
Well, physical significance, X has become equal to zero, right? It's completely washed out. There is no cells at all.
Right.
So basically, what and the physical meaning is essentially you have made. I mean, if you take a look at the balance for X, you're growing cells at the rate mu times X, and you're removing them at the rate D times X. Now, mu has a certain upper limit. If you make D bigger than that mu, you're drawing out cells faster than the fastest rate at which the cells can grow. So if you make D bigger than that value, it will become equal to zero. And my question is, what is that value of D? Well, that value of D is
Yes, sir. Now it
mathematical.
makes sense.
Because the maximum rate at which the cells can grow, given that the feed concentration is SF, is just mu m times SF over Ks plus SF. They can't grow at a rate faster than that, right? Are you with me?
Yes, sir.
So that is these are the things you need to sort of remember that according to this model, the cell density has the picture where it is kind of flat and then comes down, and the substrate concentration kind of goes up. Now, what we see in actual data, as I pointed out, is not the red-shaped cell density curve, which is what the model predicts, but the data actually shows that the cell density changes as shown by the blue curve here. This also maybe I should show. I can find. Uh, oh no. Hmm, strange. Um, I don't think I have it right off the bat. Um, oh, here it is. So this is what the data, this is the theory, and okay. So this is what the data looks like. Um, um, this is also not so great. Um, Gets me into new, so maybe we'll skip it anyway. I think I'll have to do it not quite perfect. Okay, so what we want to get to now is how to correct this model, and that forms the starting point of uh, needing to change the model, and that gets us to the beginning of what are called uh, basically you need not one but multiple reactions. Multiple reactions to capture the behavior. And the reason, as you will see, is that not only this example, but also one or two more that we will consider, most of the departures from this model involve the fact that the stoichiometric coupling fails. It doesn't hold. And so you're compelled to add another reaction. Because if you have only a single reaction, you always have stoichiometric coupling. You're going to treat anything like a reaction, a single reaction, everything is stoichiometrically coupled. Now, as we have already shown, I think I pointed out, your substrate uptake rate, oxygen uptake rate, these were not tightly coupled to growth because these rates were not directly proportional to D. They had a positive intercept. So what this guy Pert proposed, this is his first model from, this is from 1965. What he first proposed was, as I had mentioned last time, the dashed blue line is the data over here, which I have called RS observed. And the white straight line passing through the origin is what is predicted by the model. No? And what he said was, to resolve this discrepancy, I will split the uptake rate into two parts, and one part will be directly proportional to P, that will be growth, and one part will be like a flat constant part, which I will attribute to um, uh, what he called maintenance. So essentially what he's saying is, roughly speaking, he's modeling his uptake rate in this fashion. He's saying my total uptake rate is not, he has to admit it, right? That's what the data is showing. But the explanation that he gives is, let's maybe proceed with it. He assumes that he has not one reaction, but two reactions. One reaction is growth, and the second reaction is maintenance. So the first reaction here, this one is growth, which is what we have considered until now. And this second reaction, which involves nothing but, um, actually you might even put over here, to make things more general, you might also add over here S plus O2, uh, and it burns to energy in some way, shape, or form. And this is what he calls maintenance. Now, growth is assumed to follow the original kinetics, whatever Monod proposed. But maintenance is assumed to follow zeroth order, zeroth order kinetics, which means that it is always happening at a fixed rate n. And notice that the units, uh, this is kind of a little bit weird. M is describing the rate at which substrate is being consumed. So M has units of substrate, grams of substrate consumed per gram dry weight per hour. Okay. Whereas the upper one, the first reaction, is described in terms of the amount of biomass formed. This second one is described in terms of the rate at which the first entity is consumed, which is the substrate. Okay. Usually, if you are talking about oxygen, then they will shift this one to oxygen. They'll say moles of oxygen consumed per gram dry weight per hour, and then they will call it MO2. So I should just put a quick box over here. What is it that is being consumed during the process of maintenance? It could be substrate, it could be oxygen, what have you. Now, once you do that, it automatically accounts for, I mean, the very manner in which you have written these rates they automatically take care of the deviation of the rate from the predicted rate, in the sense that almost by definition, you can see that you will have a constant plus a growth dependent uptake rate. So your uptake rate is already accounted for. That part clear? I mean, this is so trivial that are you able to understand what I'm saying? That the discrepancy between the observed, this is the observed one, the dashed line, and the white line, which is passing through the origin, the discrepancy that is observed is automatically taken care of the moment you propose this model. Because, maybe I'll push it further. So now, let's proceed further. I should say that. So what is the specific substrate uptake rate in this new model? Well, it's pretty simple, right? According to this new model, substrate is being consumed for two purposes. It is being consumed not only for growth, but also for maintenance. So your RS, let's call it total. Is equal to the RS which you are using originally. I'll just keep it RS for growth, plus or maybe I should introduce new notation here. So let's just keep it as, it will be RS, which we knew earlier, plus M, where this RS, which is equal to Y excess times mu plus M. So essentially, you can take a look at this. I'm basically saying that the total substrate consumption is the substrate consumed for growth here, plus the substrate consumed over here for maintenance. That is all there is to it. Y excess mu S plus M. So maybe I should just write it. This is Y excess times mu of S plus M. And the physical meaning is this is specific substrate consumption rate for growth, and this is specific substrate consumption rate for maintenance. Okay, so now we're ready to plug this into the model and everything. So it's a very minor modification of the earlier model. Our earlier model said dAs dt equals mass balance equations, of course, always remain the same. Only the kinetics have changed. These are our mass balance equations. And at steady state, the derivatives are zero. Now, what we are assuming here is that mu is still equal to what we used to assume earlier, which is mu m ks s divided by ks plus s. But now we're assuming that rs is actually y xs multiplied by mu plus a constant quantity called m. That's it. Okay. So you can see straight away from this equation, if I call this equation 1 and call this equation 2, the equation 2 we have right now is no different from the equation we had earlier. And earlier, looking at that equation, so 2 implies, we've already done this earlier, that S is equal to Ks divided by D over mu m plus D, because it's no different from what we had earlier. But X is no longer the same. Why? Well, go back to equation 1. So take a look at, if you recall what we did to get X, we actually multiplied equation 1 by, you know, uh, y-axis and then added that to equation 2, and but all that stuff will not work right now because the terms will not cancel out. So taking a look at equation 1, you can see that basically equation 1 implies that x is equal to d times sf minus s divided by rs. Okay, that's obvious. That's just true from the mass balance. Now earlier, our rs was simply equal to y-xs times mu, right? Which can also be written as mu divided by y-xs. So let me just point out here, earlier rs was simply equal to y-xs times mu, which is equal to mu divided by y-xs, right? Which if you put into this upper figure, you can see that this gives you x equals d divided by sf minus s divided by, and this is just mu divided by ysx. But since mu equals d and d cancels out, and this will simply give you what I had given to you earlier, which is y times sx multiplied by sf minus s. But now you don't have rs equal to yxs multiplied by mu. Now you have rs equals yxs multiplied by mu plus m. But now rs equals yxs times mu plus m. But this implies that x is equal to d times sf minus s divided by, this becomes mu divided by ysx plus m. I have an additional term here. Okay, and my mu is still equal to d, right? Equation 2 still tells me that mu has to be equal to d. So this is essentially equal to d times sf minus s divided by d divided by ysx plus n. That's the expression we have. Okay. Now it's kind of convenient to rewrite it in a slightly different form. I mean, it's useful to so multiply both numerator and denominator by ysx, right? So if I multiply numerator and denominator by ysx, I get ysx, right? Multiplied by d divided by, in the denominator here I get d plus m times ysx. I take this whole thing together and multiply that by sf minus s. And this whole quantity I call ysx observed. This is just a defined quantity. Now, basically, what this is saying is, first of all, you can see that when I had no maintenance, this was my expression. It was ysx, which is the stoichiometric coefficient defining how much biomass is produced per gram of substrate. Now, instead of ysx, I have a quantity which is ysx multiplied by d divided by d over m multiplied by ysx. It's a quantity that I call the effective or the observed yield. And notice that it is a function of d. Okay. So, and it says that when d becomes really, really small, then this quantity goes to zero. So, if I plot as a function of d, you can see that y as x observed is going to be hyperbolic. It's going to be like this. And it will reach its maximum value y as x, right? When d becomes really, really large, and it will reach half its value when d is equal to m times y sx. When that happens, the value here is y sx divided by 2. Okay? So what does this thing mean? Well, what this quantity is showing to you is that physically. So what really happens is that as you, back to this model here, see what's happening here is that as, see, d is equal to mu, right? So d, as you decrease d, mu decreases, right? So if you take a look at these two reactions, 1 and 2, reaction 1's magnitude depends upon the prevailing d. The smaller the value of d, the smaller the rate of this reaction. But reaction 2, being a zeroth order reaction, has a constant magnitude regardless of the value of d. So basically, the second reaction will not be significant at large d, because at large d, mu is large, and therefore reaction 1 is much, much faster than 2, and this maintenance doesn't even show up as anything significant. As the value of d becomes smaller and smaller and smaller, the first reaction, which is responsible for producing biomass, also becomes smaller and smaller. And when it becomes sufficiently small, then basically reaction 2 dominates, and reaction 2 does not produce any biomass at all. So basically what you would expect is that at small d, the whole situation is dominated by the reaction, which is not producing any biomass, and therefore you should not see x as having significant values. And that's exactly what this is showing you here. What this is showing you here is that when d goes to 0, x goes to 0. It has to, because you can see from this expression over here, ysx times d over d divided by mysx. And what is the significance of this m times ysx? Well, this m times ysx is giving you a sense of what is the magnitude of d at which the maintenance effect is significant. So that kind of depends on m. But remember, m had units of substrate consumed per unit dry weight per hour, whereas d has units of dry weight produced per dry weight per hour. So for the units to be consistent, it's clear that m has to be multiplied by ysx. You can view m times ysx as that growth rate, that specific growth rate that you lost because maintenance took place. If this maintenance had not taken place, you would have obtained this additional quantity m times ysx of specific growth rate. It was lost because the cells were compelled to maintain themselves. So you can now see that this model actually explains both of the things. I mean, so if I were to go back to this plot here, I think I mentioned to you that the red curve is what the Monod model predicts, and the blue graph is what is observed. The blue graph shows you that X is coming down rapidly at low D. That rapid decline will be predicted by this modified model of PERTS, and the decline of X at low D will basically take place because at low D, maintenance starts to become much larger than growth, which basically means that you are using up more substrate to produce no biomass as opposed to using the substrate to produce biomass. Is that part clear?
Yes, sir.
So, uh, this quantity I have called YSX observed. You see, this is another way to say it is actually you have this YSX observed is not really a stoichiometric coefficient. This is like going to equations 1 and 2 and saying that actually just tell me what is the net biomass produced based on the total substrate consumed, right? So it's like forcing yourself to get a stoichiometric coefficient out of two equations, you really can't get one. Now, in the literature, this is referred to often. This is referred to as the true yield. And this lump quantity here is referred to as observed yield of biomass. This is the true yield of biomass. Okay? And you can see that basically it is a hyperbolic function. Now, if you have done any course in enzyme kinetics, then you know that uh, people often use um, reciprocal functions to calculate. So, is this? Uh, are you familiar with Lineweaver-Burk plots?
No, sir.
Uh-huh. So, whenever you have, let's take this case. This will appear. So I'll show it to you in two because this thing appears again and again and again. So let's say this case. Actually, let me do multiple cases here. So first, let's start. So I'm showing you a general principle of how to get from the data, how to get the parameters. So let's take case one. Let's say mu equals mu m times s over ks plus s. Okay, and let's say you want to measure, you want to find out mu m and ks. Notice that it is a hyperbolic function. Okay, and in a chemostat, you kind of know that mu is equal to d. So I can actually put this as equal to d here. Okay, in a chemostat, this has to hold. So supposing I do a bunch of experiments at different d's in a chemostat, and I find out what is the value of the steady state substrate concentration at various values of D. So some D1, D2. So this is basically, I have this kind of data. This is D and this is S going up. I'm measuring it at various values. So this is D1, D2, so on and so forth. And these are the corresponding values of S1, S2, S3, and S4. So how would I find out the values of mu m and ks from this data? I mean, this is extracting the parameter values. Well, one standard method is, whenever you are given a nonlinear function, first try to put it on a form where it becomes linear. And that means in this case, in the case of a hyperbolic function, take the reciprocal. So this becomes 1 over d on this side, and here it becomes 1 over mu m and here it will become Ks plus S divided by S. But this can be written as equal to Ks divided by mu m multiplied by 1 over S, right? And this becomes 1 over mu m. That's it. So what I have is the relationship 1 over d equals Ks divided by mu m multiplied by 1 over S plus 1 over mu m. So if I were to plot from the data, I have the data now. If I were to plot 1 over t versus 1 over S, what I should get is a straight line with a positive intercept. So my points on the upper graph will actually reduce to a graph of straight lines. This graph now allows you to find out the values of Ks and mu m because its slope is going to be equal to Ks divided by mu m and its y-intercept is going to be 1 over mu m. So there are many problems on the homeworks that I'll be giving you today of this kind, finding out the values of the parameters. So far, so good? You follow what I said?
Yes, sir,
Yes,
it
sir.
makes sense.
Okay, so now take a look at the other function here. This is the same principle again. 2. I have shown you the relationship y(sx) observed is equal to the true yield multiplied by d divided by y(sx) times m plus d. I mean, so it's formally the same as a hyperbolic function shown above. If I knew the value of y(sx) observed, okay, and I'll get to this in a minute. How do you find this? If I knew the value of y(sx) observed at various values of d, then I could use the same method to find out y(sx) and m. Are you with me so far? Just take the reciprocal of both sides, yeah, and then plot the data. I mean, what I'm telling you is that if somebody gave you y(sx) observed versus d, if somebody gave you this data, right, as a function of d, you could do the same thing, right? I mean, it's a hyperbolic function. Take the reciprocal of both sides, and you're done. Are you with me?
Yes, sir.
Total silence here. I mean, I have no idea. Now, actually, people use this method to find out the parameters of Pert's model. I mean, I have to show it to you because to me it seems like a really stupid way of doing it, but it's all over the literature, so I have to show it to you. So, first of all, how do people find out this y(sx) observed? Well, if you think about it, your y(sx) observed, right, is actually uh, uh, huh, huh. See, um, actually, I'm trying to show that d divided by that's it. So this equation is clear to you, right? This comes straight out of the mass balance. Is that part clear to you?
Yes, sir.
Yes, sir.
Now take a look at this part, and you can see that basically what I have called y(sx) observed is nothing but d divided by rs.
Yes, sir.
This is, as you can see, nothing but YSX observed. So YSX observed by definition, is nothing but the value of D divided by the corresponding value of RS. Okay, that's what, they've just decided to call this a name, to give this a name. They've called this YSX observed. Are you with me so far? They could have given it any other name. So you can now see that basically this quantity YSX observed is a measurable quantity. Why? Because at every D you can calculate RS, right? I mean, RS, as I told you, can be calculated. If I give you D, then RS can be calculated as D multiplied by SF minus S divided by X. So, yes, so YSX observed, go down here. This quantity is nothing but D divided by RS. The observed RS, whatever RS you actually see, right? And this you can measure. You can each of these. So at every D, you can find out what is the rate at which you are consuming the substrate. This quantity is measured by simply calculating D multiplied by SF minus S divided by X. So this is nothing but the quantity, the ratio. D divided by RS is nothing but SF minus S divided by X. Observed. You measure this, you measure this, you measure this, you take the ratio. That ratio is basically equal to D divided by RS, which is defined as Y observed divided by SX. So it can be determined from the data. Are you with me so far?
Yes, sir. It's understandable.
So once you get this kind of data, then you can take 1 divided by Y SX observed. It will be equal to 1 divided by YSX multiplied by YSX times M plus D divided by D. And that implies that 1 over YSX observed equals, this becomes M times 1 over D plus 1 over YSX. So basically, if you plot this data, this data, the top graph, which is showing YSX observed divided by D, this can be obtained from, this is basically SF minus S divided by X. So as you experimentally measure various S and X at various D, you measure the S and X at various D and get this data, then you replot this data as 1 over YSX observed versus 1 over D. And what you should get, if the model is correct, is the data should reduce to a straight line having slope equal to M and y-intercept equal to 1 over YSX. So this is actually, um, this is the way people often do it. And actually, when I showed you that paper by Pert, this is what he's doing. So, um, where is it? Right. So, do you see 1 over y on the y-axis and 1 over mu on the x-axis? You see that?
Yes, sir.
So this 1 over mu is basically 1 over d. And what he has called 1 over y, what I have called 1 over y observed. This 1 over y observed here, this y observed is nothing but d over rs, which is equal to, as I've just told you, sf minus s divided by x. So it's a measurable quantity. So he basically took the data of people and then plotted it in this way, showed that it is a straight line, and confirmed that his model is correct. So he's basically saying that look, all the data fits to 1 over y versus 1 over d being a straight line, which means basically that y is increasing hyperbolically with mu. That part clear?
Yes, sir.
Okay, so um, I think you can. This basically covers. So I should just mention. Yeah, I have 2 points to mention about this stuff. Um, so this model fits the data quite well. As I just showed you the papers, and I mean, if you take a look at this paper, it has, I suppose, hundreds, if not thousands, of citations. Um, but it highlights a major problem, um, uh, which I think, let me see if I can point out. Um, ah, okay, okay, all right. So let's take a look at the equations as I have written them down here. Um, Suppose I want to use this Pertz model in for a shake flask. For a shake flask. All right. That means that um, D is basically equal to 0. So that means that I'm going to neglect this term as well as this term. So my model is essentially ds dt equals minus rsx, and the derivatives are not equal to 0 because I'm applying them to a batch reactor, right? So things are changing. You can't put the derivatives equal to 0 anymore. And dx dt is equal to mu x. And now mu s is still the same. It's mu m times s over ks plus x. But my substrate uptake rate is no longer just y xs times mu, but it also has a constant term plus n, right? So y has this term plus n. Can you see any problem coming up? If you do this simulation in time, let's say integrate this model, right? Numerically. And what it'll start to do is basically you start off with some initial substrate concentration and some initial cells in the shake flask. And then, the cells grow and the substrate is consumed. So the biomass is going up, the substrate is coming down, and it's coming down and it's coming down and coming down. And let's say S becomes really small, it approaches 0. Can you see what can go wrong with this model there?
So when a S approaches 0, like mu would approach 0, but M would not approach 0. So,
Uh-huh.
but the
That's good.
substrate isn't there, so how would they maintain themselves?
Right. So basically what happens is that if you put it into a computer, what will happen is you have ds dt equals minus rs times x. The first term of this rs will have gone to 0 because there is no substrate and therefore there is no growth. But this m keeps pulling substrate. So your numerical simulation will take the s to negative values. You'll start seeing negative values of s. Okay? I mean, is that part clear? Actually, so the rule of thumb is that uh, a reactant, you should never actually have zero. This is a standard problem with zero order reactions. If any time you put a zero order reaction, the substance continues to be consumed even when that substance has, there is no substance available. I mean, just write an equation. dx dt is equal to minus k, and that's it, right? It has to go to negative numbers. So actually, people never use zero order reactions for this reason. I mean, it has a pathological behavior, but in the biological world, I think people's understanding of differential equations is somewhat so rudimentary that it took, I think, almost a decade for people to even understand this was a problem. Uh, so anyway, so that leads us to an alternative model, which I will give to you and let you try out on your own. Like so this is the problem with Hertz model. So I should mention that despite this deficiency, it is widely used because this deficiency only appears in batch reactors. In a continuous reactor, you will not see it. You know, this does not happen. So anybody working with chemostat simply ignores the fact that this is a potential problem and moves on. Um, if applied, if applied to a batch culture, it it yields God, it yields negative substrate concentrations after a after substrate is exhausted. So now the alternative which does not have the alternative model, which explains all the things that are explained but doesn't have this problem, commonly goes by the name of Herbert's endogenous. It's called Herbert's endogenous metabolism model. So it's a slight variant actually. Now what this model says is, it says that once again I have S y excess and plus oxygen or what have you going to X, and this is happening at the rate mu. Okay, and mu is some function of S. But now, and this can also produce other things. But now, instead of using up the substrate, right, in the second reaction, what Herbert proposed is that basically there is endogenous metabolism, meaning the cells use up themselves to support maintenance. So, stated differently, it would be as if they used up their carbohydrate reserves or their fat reserves. They broke them down, or they started breaking up their proteins to produce the energy that is required for maintenance. So that means that basically the second step has the form X goes to, this just burns up to CO2. And this is maybe given the symbol mu prime, where mu prime is a constant. So a constant product formation rate actually does not give problems. It is a constant reactant consumption rate that leads to problems. So now I suggest that you try this out on your own. This is a minor modification, right? And see for yourself uh, what are the differences in the results that you get from this model. Well, as I'm pointing out to you, there are this model will also account for the fact that the substrate consumption rate is not directly proportional to D. It will have a positive y-intercept. It will capture that data properly. However, the concentrations of the substrate will turn out to be different from those that you got in PERT's model. But if you want to develop some modeling skills, then now that I have done a model, how hard can it be to just do the same thing for a slightly different model? Apply the same principles and see what you get. So this I will leave for you to do as an exercise. It's the same thing. Uh, mu of S is equal to mu m times, and whoever does it can maybe present it next time. Uh, if you're successful in doing it, you can volunteer to present it next time. So you can see the general principle that has emerged is that whenever the rates do not have stoichiometric coupling, you have to move away from the Monod model. You have no choice. That's just the way it is, because the Monod model in, intrinsically assumes stoichiometric coupling. Now, the last part, actually last but one part, the third part I'll not cover in any detail, is another example, another they all form in the same class. So, like I should say, um, failure. So first I have shown you the failure of the model at low dilution rates in a continuous culture. Failure of the Monod model in cultures limited by more than one substrate, more, let's just say, multiple substrates. So actually we'll be looking at only two. There's no need to go beyond that. Actually, two already takes you to state of the art. Meaning, people are still grappling with understanding what happens when cells grow on two growth limiting substrates. So the best way to explain this is to maybe um, just show you the data. I mean, what does the data look like? So these are experiments that were done maybe 25, 30 years ago. Um, and they clearly show that the Monod model is bound to fail. So just taking a look at the data will just show it to you. There's no need to do any modeling or anything like it. So let me see if I can um, show this to you. Um, um, it is actually so this might be good data to look at. Actually, maybe I'll take another one because it's of practical value. So I'll take a look at this one. So this is showing you um, this is an experiment that has been performed in a chemostat at so the each let's just focus on one panel, right? So let's take a look at, for example, this panel over here on top where it says zero point 0.4 per hour. So this experiment was performed in a chemostat. The dilution rate is fixed at 0.4, and on the x-axis he's basically showing you the concentration of carbon in the feed. Actually, what he's showing is T0 to N0 in the medium feed, which is basically the carbon to nitrogen ratio so the ratio of, say, glucose to ammonia in the feed. But since the concentration of ammonia is fixed, effectively this is nothing more than you are keeping the nitrogen concentration fixed, and this experiment is being performed in a chemostat at progressively higher concentrations of the carbon in the feed. Okay, so you have, if I can say it here, fixed nitrogen ammonia concentration in feed. You also have fixed D, the dilution rate is fixed, and you just keep on increasing. You do one experiment with, say, 1 gram per liter of the carbon source, then 2, then 3, then 4, then 5, and at each of these you measure the steady state. So I mean, I'll give this to you in a very intuitive way, but intuitively you can see that when I am providing a very small amount of carbon in the feed, so way to the left, you expect the growth to be carbon limited, because that's what's in shorter supply. And if you have made sure that all the other stuff is in excess, then basically at a sufficiently large, as you keep on increasing the carbon supply in the feed, there will come a point when something else will start limiting, because you are progressively increasing the carbon in the feed. So as you keep on increasing, there will come a point when the carbon is in excess and something else has become limiting. And you can always arrange what that other substance might be. The people who did these experiments made sure that nitrogen was limiting when the carbon became sufficiently large. So way to the right hand side, the growth is nitrogen limited. Okay? So basically what you have is, to the left you have carbon limitation, to the right you have nitrogen limitation, right, as you do this experiment. Now the main point I want to make before I close the lecture is that this transition from carbon limitation to nitrogen limitation does not take place abruptly. By abruptly, I mean it does not take place immediately at some particular value of the feed concentration. There is an entire range of feed concentrations in which there is both carbon and nitrogen limitation. The limitation by both substances. There's a dual limitation. These areas are shown in this paper by a shaded part. So you can see that at D equal to 0.4, there is a thin shaded part. At D equal to 0.3, that shaded region becomes a little bit thicker, and then a little bit more thicker at D equal to 0.2, and so on and so forth. The main point I want to make is that the transition from carbon to nitrogen limitation takes place. There is a region in which there is a transition. It's not an abrupt change from one limitation to another limitation. Now, intuitively, you can see that the Monod model is screwed in this transition regime. Why? Because I told you that the Monod model typically works for limitation of any kind. It could be carbon limitation, it could be nitrogen limitation. But the stoichiometric coefficients are different. So for carbon limited regime, for example, the carbon is used very efficiently. But in the nitrogen limited regime, it's the nitrogen that is used efficiently. So the yields, the so-called stoichiometric coefficients, are different in these two regimes. And the transition regime, which is the shaded region in the middle, is the region in which these stoichiometric coefficients gradually change. They change from those values associated or typical of the carbon limited regime to the values that are typical of the nitrogen limited regime. So, almost by definition, the stoichiometric coefficients are changing. There is nothing you can do about it. I mean, that's the purpose of this regime. Are you clear? That's, I mean, we'll get to it in more detail later on, but I just wanted to make the claim because the moment the stoichiometric coefficients change, you know that the Monod model is going to fail. Is that part clear? I mean, I'll discuss
Yes, it
this
makes
data
sense.
in more detail next time, but that's the basic point. Okay,
Yes, sir.
and we'll pick up on it next time. So I think I have two more lectures, and then we'll finish off this section.
So I had one more question. Sir, a small doubt. Like, so for example, imagine you have a substrate as glucose, and then the cells start performing some sort of a gluconeogenesis. Like they start producing more glucose. So in that case, what happens?
If the substrate is glucose and they start producing more glucose, well,
Yeah, sir, it can happen, right? Because like they consume like pyruvate and then like basically they make glucose from pyruvate,
well,
like
but that,
gluconeogenesis.
but to make glucose, but to, but the, but no, you have to talk about the net rate of formation, right? Meaning, if they are consuming glucose, then certainly glucose is undergoing glycolysis, right? So it is getting converted to uh, via hexokinase. It is going down the glycolytic pathway. Simultaneously, there may be gluconeogenesis, which means it might be going upwards. The scenario that you are projecting, which is formation of glucose, can only happen if the rate of gluconeogenesis exceeds the rate of glycolysis. Are you
Right.
with me? Um, that would be, it seems to me. I mean, I'm not aware of any situation in which that happens, and the reason why that cannot happen, certainly during growth on pure glucose, is that I think the energy required for gluconeogenesis is more than the energy required for glycolysis. I'm not mistaken because you use more ATPs to execute the reverse process. So I mean, if you have both
Yes, sir.
things going on simultaneously, you're not generating any energy at all, unless and until. I mean, it could happen, but I'm not aware of any system in which there is net generation of glucose. Meaning net meaning it is exceeding the amount that is breaking down. Do you follow? The net is
Yes, sir.
always in the downward direction.
So
Uh,
in some case, like for example, there is glucose, and the cells initially started growing and metabolizing, and after a point of time, when the glucose concentration decreased to like significant amount, like insignificant amounts, and the cells basically
uh,
stopped growing, but then they started producing
uh,
glucose.
no, that's possible, right? Uh, but then they are probably consuming something that was excreted while they were growing on glucose. Uh,
Right, sir.
uh that's possible. So the simultaneous operation of glycolysis and gluconeogenesis is kind of well known, and people have actually, there's an entire area where they have. It actually leads to tremendous wastage of energy, and people have tried to study why this is there. It's called futile cycles. You just do a search on futile cycles, and you'll find. But I don't know of anybody that has shown net production of glucose while glucose is the substrate. what they have shown is that there is net consumption of glucose. The glucose goes down, and there's stuff coming back to glucose, but the rate at which it goes down is bigger than the rate at which it comes up back to glucose.
Right, sir.
That's the level at which I'm familiar with the stuff. Okay. Any other questions? So I think the rest of it, there are ample questions in the homework sheet that I'll put there. It'll keep you busy for a while. Okay. All right. So I'll see you on, I guess,
Sure,
Saturday,
sir.
right? That's the makeup.
Yes, sir. Yes, sir, Saturday. Thank you, sir.
Thank you, sir.